In the solar system, there are many truly unusual bodies. Io, with its countless erupting volcanoes, Titan with lakes and seas of liquefied gases, Pluto with nitrogen glaciers, the two-faced Iapetus, Miranda with terrain that looks as if it were stitched together from patches. And that's far from all. There are plenty more examples. It's not surprising that a seemingly inactive gray lump like our moon might appear boring to many people, especially since it's always right there. We've seen it hundreds and thousands of times. But the idea that the moon is boring couldn't be further from the truth. The next time you look at the moon in the sky, pause and think. Doesn't it seem strange? Special? As if something about it is off? And in fact, it really is strange and special, and in a certain sense, something really is not quite right about it. There are many unanswered questions about the moon. Our moon is unique in many ways. Earth has exactly one natural satellite. Other planets either have several, sometimes dozens, or none at all. Moreover, the moon is the only large satellite of a terrestrial planet in the solar system. And yes, the moon is big. It's not the largest satellite in the solar system. It ranks about 5th by size, but the word only feels inappropriate once you look at what's larger than it. Those are moons of giant planets, planets that are themselves many times larger than Earth. And yet the moon doesn't lag far behind the largest moons in absolute size. The moon has a truly unique size ratio relative to its planet. If you compare Earth and the moon with, for example, Jupiter and Ganymede, the difference becomes obvious. The moon's radius is more than a quarter of Earth's radius. We don't see a satellite this large relative to its planet anywhere else among the 8 full planets, leaving dwarf planets aside for now. That's why some people refer to the Earth-Moon system as a double planet, which we'll discuss later. Such an unusual size ratio immediately raises many questions. Why did it happen? What does it mean? And how did it come about? Clearly, the moon's size is linked to how it formed, and its formation appears to have been quite unique compared to most other moons. In the inner solar system, rocky terrestrial planets generally have very few moons. Aside from our moon, there are mainly Phobos and Deimos orbiting Mars, but those two irregular lumps are almost embarrassing to compare with the moon. Their sizes are measured in tens of kilometers, while the moon's diameter is nearly 3,500 kilometers. The dozens or even hundreds of other moons we usually compare against belong to the giant planets. We're also limited by what exists in the solar system. As of now, there are no confirmed exomoons, moons orbiting planets outside our solar system. Only a few candidates. How do moons form around giant planets? One major scenario resembles planet formation around young stars. Some of the material that doesn't become part of the star forms a protoplanetary disk within which planets form. Giant planets can, in turn, form their own smaller disks from leftover material, and moons form within those circumplanetary disks. Evidence for this includes the fact that many moons orbit roughly in the plane of their planet's equator. Another formation pathway is gravitational capture. Objects that formed elsewhere are later captured by a planet. Such moons often have highly inclined orbits and can be significantly elongated. Captured objects can be small, like asteroids, or quite large, such as Triton, Neptune's largest moon and one of the biggest in the solar system. But the moon, as far as we understand, formed differently. Other scenarios have been proposed, for example, material being torn off a rapidly spinning planet. But the most widely accepted modern theory is the giant impact hypothesis. According to it, the moon formed from material ejected into orbit after a collision between the proto-Earth and another protoplanet roughly the size of Mars. I've discussed this model many times and even made a dedicated video about it. In other words, the moon did not form the way most moons do. If we draw an analogy between star-planet and planet-moon systems, the general pattern is that the primary object is vastly larger than its companions. There are rare exceptions, such as massive planets orbiting small stars, but those are special cases still under study. Under typical formation scenarios, like accretion in a disk producing a moon as large as ours, is very unlikely. A collision between two large bodies, however, can plausibly leave behind two objects with mass and size ratios similar to Earth and the Moon, but even that isn't the whole story. Large planets don't always form proportionally large moons. Researchers have run computer simulations of protoplanet collisions to see what kinds of disks form and what satellites can emerge. These studies focused on rocky terrestrial and icy planets. Mini Neptunes and gas giants were not included. An important detail: in the standard picture, a collision ejects material into orbit, forming a disk. For the Moon, this disk is thought to have been partially vaporized, with some material in gaseous form and the rest as fragments of various sizes. Simulations show that collisions don't always produce partially vaporized disks. Sometimes the disk becomes fully vaporized, and in such cases, a large moon cannot form. Instead, small, mini-moons ranging from hundreds of meters to tens of kilometers in size begin to form. Gas drag causes their orbits to decay quickly. They merge or fall back onto the planet, and no large satellite has time to grow. Fully vaporized disks tended to form around more massive planets, rocky planets above several Earth masses, and icy planets at even lower masses. The reason is straightforward. More massive collisions release more energy, increasing the chance that the material vaporizes completely. If these conclusions are correct, they could help make the search for large exomoons more efficient. They also make our moon even more exceptional. Even the giant impact scenario alone does not guarantee a proportionally large moon. Very specific conditions are required. Now, let's return to the idea of a double planet. In 2003, the European Space Agency published an article with a headline along the lines of, "The Moon, Welcome to a Double Planet." It claimed that Earth and the Moon are not merely a planet and its satellite, but a double planet, with the size ratio being one of the main arguments. The problem is that this is largely a matter of terminology. To get a clear answer, we need clear definitions. What exactly is a satellite and what is a double planet? The International Astronomical Union, IAU, provided an official definition of a planet in 2006, the one that famously stripped Pluto of its planetary status, but it does not provide an official definition of a double planet. In fact, it doesn't even offer a strict definition of a planetary satellite. As a result, there is no formal way to prove that Earth and the Moon constitute a double planet. There are no official criteria, only informal approaches. One such approach is based on mass. If two bodies have comparable masses, they could be considered a double planet. But Earth and the Moon differ greatly in mass. The Moon is about 81 times less massive than Earth. Another commonly cited criterion is the location of the barycenter, the center of mass around which both bodies orbit. In typical binary star systems, the barycenter lies in empty space between the stars. In the Sun-Earth system, the barycenter lies inside the Sun, very close to its center. In the Pluto-Charon system, however, the barycenter lies outside Pluto's surface, which is why Pluto and Charon are often described as a true binary system. For Earth and the Moon, the barycenter lies inside Earth, though not at its center, about 4,650 kilometers from Earth's center, given Earth's average radius of 6,371 kilometers. By this informal criterion, Earth and the Moon don't quite qualify as a double planet, whereas Pluto and Charon do. But that leads to another paradox. Under the IAU's 2006 definition, Pluto isn't even a planet, so calling it a double planet becomes problematic. The conclusion is simple. There is no official definition of a double planet, no universally accepted criteria, and under most informal definitions, Earth and the Moon are still best described as a planet and its satellite. While researching this topic, I came across an intriguing twist. There exists a viewpoint, even presented in the form of a paper, suggesting not that Earth and the Moon should be called a double planet, but that the Moon itself should be classified as a planet, the 9th planet of the solar system. The argument goes roughly as follows. The Moon clearly meets the criterion of hydrostatic equilibrium, being spherical. The debate then centers on the remaining criteria. Orbital clearing in the Earth-Moon system is largely handled by Earth. The key subtle point is orbiting the Sun. Instinctively, one might say, but the Moon orbits Earth. However, when viewed in a heliocentric frame, the Moon's trajectory is very close to Earth's orbit. Without the looping paths often shown in simplified diagrams, Earth merely causes small oscillations. Sometimes the Moon is slightly closer to the Sun, sometimes slightly farther away, but the difference is tiny compared to the overall distance. The next step in the argument is gravitational dominance. It turns out that the Sun's gravitational pull on the Moon is several times stronger than Earth's, unlike many moons of giant planets, which are much more strongly bound to their planets. From this, the authors argue that the Moon effectively orbits the Sun in a sufficiently direct sense to satisfy the criterion. It's an interesting line of reasoning, but in practice, no one is rushing to officially reclassify the Moon as a planet. There are also concerns about where the paper was published. The publisher has a questionable reputation, which doesn't automatically invalidate the arguments, but does warrant caution. Still, the discussion highlights how vague some of our definitions are, and how useful it would be to refine them. Finally, let's address these strange craters often cited by conspiracy theorists. One popular claim is, why are all lunar craters the same depth? From this, some conclude that the moon has a thin regolith layer on top and a solid artificial shell underneath, sometimes even imagined as a metallic sphere. The problem is simple. The premise is false. Lunar craters are not all the same depth. Large craters can be several kilometers deep, some reaching 4 to 5 kilometers or more, while small craters may be only tens of meters deep. There is no uniform depth. A more accurate version of the question is this. As crater diameter increases, the ratio of depth to width decreases. Large craters appear flatter, while smaller ones look deeper, like bowls. This is completely normal impact physics. To form craters tens or hundreds of kilometers across, the impactor must be enormous and moving at tremendous speed. At such energies, rock behaves like a fluid. Material melts, flows, collapses inward, and gravity smooths the result. Lunar gravity would not allow deep cavities comparable to a large fraction of the moon's radius to persist. If large craters were proportionally deeper, the moon would look badly distorted, but gravity always pushes large bodies toward equilibrium. So no matter how you look at it, I could never bring myself to call the moon a boring gray rock. And even though I've talked about it a lot already, there's still an incredible amount left to explore. If you enjoy videos like this, I'll be happy to continue.